can carry the roads heavy traffic and something like that also. And when the water have to go to the route soil planner and then get through to the groundwater. That's the whole idea in it. But we knew there was some problems with its carrying layer because the traditional carrying layer here we use in Denmark is something called stabilgrus. They have a problem with water. If they get water, they lose a lot of the carrying capacity. So we have to make a new carrying layer, and that's why this drain stabil started. Drain stabil is a new carrying layer who can take the water and also take the carrying capacity from the traffic. If you look a little bit here, we can see at the left-hand side, we have this traditional carrying layer called stabilgrus on Danish. And for the right side, we have this new one called drain stabil. And now I say new one, it's we started with it in 2011, so we know it today, and we have a lot of success with it. We got all the small stones away from the traditional carrying layer and got this space for water. We got up to 30% space for water. And we crossed the stones at a way so all the carrying capacity is going through the stones. So that's how we can make it, and that's how it works today. This, what I told you a little about the water. If you got water, rainwater into a traditional carrying layer, we lost a lot of carrying capacity, up to 80% in a few hours. If you use this drain stabil, the new one, we have no problems with the carrying capacity. It only falls maybe 5 or 10%, but not so much as the other one. And on this way, we can have water into our carrying layer, and we can also have a lot of the traffic at the top without some problems. For NTC, it was necessary to know the E model of the material. We have to know how much it can carry. The load capacity is necessary to know, and also if you have to make a calculation about the traffic. So for us, it was necessary to test it, and there was no firms in Denmark who can test it. So we have to go to Linköping in Sweden to make these tests and use a laboratory up there. I'll not tell you so much about that, but I can tell you the last thing I read on this one is that we guarantee we have a E-model on these about these 300 megapascal. And that's totally the same like the traditional dry carrying layer we use in Denmark. So that's how we got it tested, and that's how we use it today and say we have the same carrying capacity at this new carrying layer instead of the old one. Some pictures from the first project we make here in Denmark. The first one to the left-hand side is a project in Odense on Fyn, where they have a road was with problems for water. They get floated when we have heavy rains, and they take up the old roads, put this drain stabil on the bottom and these permeable asphalt on the top. And today is totally works still. It's more than 10 years old today. And the other pictures on the right-hand side is just for some other project we have made around in Denmark. Today, we have made more than 250,000 square meters of these, and about 50% is with asphalt, and the other things is with these concrete stones or tiles. This project is from a project in Hedensted, just between Vejle and Horsens. Little what to build a new shop there, and they got the answer from the supply management, the supply company, that they can't take any water in the pipe systems, so they have to handle all the rainwater at the place at the grounds. So the solution was to make all the parking areas in this way with permeable asphalt and this carrying layer who can take the water, and all the water from the top of the building got in some pipe systems and under this parking area and go to the drain carrying layer. And on this way, they handle all the water from this project on the ground. So no water get out from this, and today is still working. It's about 6 years old now, and they have no problems with heavy rainfalls or things like that. So that's a way how to do it, and also to make to take the water away from the roof of the buildings or something like that. Here, just a small video from rebuilt roads in Copenhagen, just to show how much water the road takes when it's totally new. Of course, after sometimes they got something dirty in it, the roads, something from the trees and other things, sand or something, and the capacity goes down. But it's not so much so we have problem with the roads. Otherwise, man can maintain it for every third or fourth year, so we can have the permeability again in the roads. And also some pictures from the Thermoroad in Hornsø, just to show how the road was building with the pipes at the bottom. But I know Søren will tell you a lot more about it. So that's just a short telling about what we do in NTC, how we make our climate roads. We call it permavej, the permeable roads, and we make it without a membrane. We make it with membranes or something like that. So that's how we do it. And on this time, we just have a project on Sjælland near Copenhagen with a new road and also with the same rebuilt existing roads to a new one who can handle these heavy rainfalls. Yes, that was all from me, son.
Okay, there's a question from Bjørn.
Yes.
Yes, I'm just asking, you said you can make a maintenance procedure every 3 years. How do you do that?
We do it with a road sweeper. And as you see, these road sweepers, you normally see at the roads this autumns of the year, something like that. But it's a little bit bigger, and they have a high pressure at the bottom of it, at the back end of the truck. So the with high pressure water, what do we call it? Clean the roads, and when we have a big vacuum cleaner at the bottom, also a very heavy vacuum cleaner to take these up again. So that's how we maintain it.
Thank you.
Yeah.
Michael, this clogging, is it only where you have where the tires normally sort of drive across road? I don't know the English term for this.
No, yeah, it is. It's normally where the tires is running. A little bit all the other places, but the most difficult thing is to clean there. We have the tires. That's right.
So there's another benefit. I don't know if you've done any measurements on it, but there's something about tire noise and these permeable asphalts. I think that's quite interesting.
Yes, it is a noise reduction layer. But if you talked with speed under 50 kilometers, you can't talk about noise reduction in asphalt. You have to have more speed. And normally we only build these roads for parking areas, small roads in the towns or something like that. It's not for heavy, big roads. So yes, it is a noise reduction surface, but you can't talk about it, son, because you have the speed on the cars is lower than this 15 kilometers an hour.
Okay. Any other questions to Michael? Do you use this technology outside Denmark? Have you done any projects in?
Yes, with a Nordic company, and I know my colleagues in Sweden have done it in the south part of Sweden. They have built one up there, and there's also built one in Stockholm also. Otherwise, we don't build in other places, but I know from England, the United States, Australia, and something they also use it a lot. Yeah.
Yeah.
Michael, you said it was a noise reduction surface. Is it the same you use on motorways I mean the top layer, is that the same you use elsewhere for noise reduction?
It's nearly the same. The construction is nearly the same. It's another receptor we use, but the idea is the same with we open the asphalt, so the noise goes through the asphalt instead of just covering the top of the asphalt. Yeah, that's right.
Thank you.
Just final question on, do you know anything about the experience when you're in different geologies? Like, is it unconsolidated sediments, altså løse sedimenter in Sweden, and is there anything to consider when you have hard rock, perhaps close to the surface? Or?
No, that's not a problem. Not a view up there, son. That's not a problem. But you have to know that I have not to be so much of the small things around the stones. You have to have a strong stones. You're not all these space for water we have in the carrying layers. It's not legal to give this fill up with small things. So you have to take care about this. But it's no problem to make it with stones from Norway or Sweden or something like that. No problems. We had also make it in Denmark some places, because we have problems with delivering of these normally stones we have in our production places in Denmark.
Okay. Any other questions? Okay. Then we proceed to Søren.
Yes, now just press this magic button, sharing in Teams, and see if it'll work. Oh, there was an issue. Wonderful. We'll try something else, because I have a very big screen, and I really don't want to share the screen, because then you won't be able to see anything. But it seems like you can do PowerPoint in Windows mode. So that works. Great. Yeah. So my name is Søren Skjold Andersen. I'm a chairman of the board of our non-profit association, Thermoroad Europe, which is a part of a national association for now at least, called Thermoroad Denmark. And I'm going to talk about the more general principles on constructing these thermonets, and then other presenters will dive into what we actually built on the Thermoroad. So just briefly about the association, we have around 158, 160 people. It changes a bit when people join and leave jobs, but around 84 different organizations who are members. A lot of the Danish municipalities, I think about a third of them, but we also have knowledge institutions like VIA, and we have Dantonite, where Michael is also representing. We have some utility companies and advisors, and a lot of different organizations. And we also have private people who are interested in this technology. So what we're doing in the association is that our main purpose is to promote thermonets, which are these collective geothermal heating and cooling systems everywhere where they can contribute to more climate-friendly solutions. And we do that we have 4 different points in our bylaws. One is getting people to meet each other by establishing these forums for dialogue. We also secure resources and initiate collaboration. We collect data and we distribute information to the public, like what I'm doing right now. So on our English webpage, thermonet.eu, we publish case stories. Right now we have 3 from Denmark, and one of them is a very elaborate case story about the Thermoroad. So I'm guessing you're getting these slides, and you can click the link I've put in bold and read a lot about the Thermoroad if there was anything in the presentations that we didn't cover. We will also publish case stories from other European countries as they arrive, as we gain knowledge of them. So that's a good place if you want to learn more about thermonets. And we do push these stories to other actors, like we are members of the European Heat Pump Association, and they wrote a bit about the Thermoroad as well on their webpage. And as Søren already mentioned, they awarded the project with the Lighthouse Heat Pump Award for 2025. And we are also members of the European Geothermal Energy Council that also publishes our stories in abbreviated versions. So you can see Søren also featured on their web page. And we want to do that for all ThermoNet stories in Europe. So we have recently added a second para to our bylaws, and what we are stating in that part is we talk about energy communities and shallow geothermal energy and collective heating and cooling. We talk about ThermoNet in these settings because we think there is an integrated solution, which the Thermoroad is a very good demonstration of how you can do the green transition in a much better way with less resource intensity and more energy efficiency if you combine these different topics. And the ThermoNet is a good way to do that. So we have our contact email here if you want to connect with the association in any way. So one example of what we have been doing recently, and what you can also see probably from some of the coming presentations, that we really enjoy making this easy to understand, partly by doing visuals. And this is a newly created visual of how you can demonstrate a shallow geothermal collective heating and cooling system combined with an energy community that produces its own green electricity. So this is a very simple conceptual demonstration, but it does emphasize what some of the benefits are, that you can have the energy source located outside of the city where there is room for it, and you can collect your energy from your electricity from renewable energy systems like windmills and solars also outside the city, and you can have the benefits of heat pumps regardless of whether you have high rises or you have single family homes. So a working definition of this ThermoNet is I'm probably not going to read everything here. I've just highlighted some parts that we're talking geothermal energy. It's the distribution of geothermal or other thermal energy, but the distribution happens at a temperature that's very close to the ground temperature, which means that the pipes in the ThermoNet are often uninsulated. And for ThermoNet as a grid, a collective heating and cooling system to make sense, you have to have more than two houses. Otherwise, you just have your own independent shallow geothermal system. And it can supply, in combination with geothermal heat pumps, it can do heating, domestic hot water, and it can also do active cooling. But as you'll hear in this project, we're more fond of utilizing the passive cooling from these systems because it saves quite a lot of electricity when you do that. And one of the other benefits is that it can act as a short-term or seasonal energy storage. It's of course at a very low temperature, but the amounts of heat you can store in the ground are quite significant. So to be very clear on the terminology, whenever I say ThermoNet, I mean a very specific part of an integrated energy system. So this is a conceptual scheme of how we use the word ThermoNet. On the left-hand side, you have the energy sources, and they can be many on a single system. It can be one on a single system. The heat can come from excess heat from energy production. It can be wastewater. It can be rainwater. It can be a lot of different things, as you also saw on the previous slide with the definition. And it can be shallow geothermal, near-surface geothermal, industry, a lot of different energy sources that can supply the bulk of the energy need for the houses or whatever you're delivering heat to. And in the middle, you have the actual thermonet. So that's the part that transports the energy to the heat pumps. And that's what I call thermonet. So it's shown here with the dashed lines, that inside all the dashed lines, you have the thermonet. On the left-hand side, it's the energy sources. On the right-hand side, you have the heat pumps. So the heat pumps are not included whenever I say thermonet. It's not a concept. It's a set of pipes. And we don't care if the thermonet supplies a very big heat pump or if it supplies several smaller heat pumps. It just has to be more than two, otherwise it doesn't make sense to call it a collective geothermal heating and cooling system. So what we have on the Thermoroad is 12 houses, each with their own heat pump. So it looks more like in the top of the picture, where you extend a smaller set of pipes to a limited amount of houses. But actually in the project area right across the street, there is another heat pump, a very big one, supplying, I think it's 15 houses from a single heat pump. And when we were building the system, we were actually hoping that we could supply that heat pump as well. So we would both have a very big heat pump and several smaller heat pumps on the same system. But they went with an air source heat pump instead because the project at that time was in a very early phase. And as it's normal in the utility business, you want to go for tested and tried solutions. So we only have the system where there are heat pumps in each and every building. But as I mentioned, we don't really care when we talk about thermonets, whether you go one route or the other. And why would you want to do a thermonet? Well, for newly built, sometimes you would like to avoid this situation where you have outside air source units at each and every house. That could be due to noise. It can be for aesthetic purposes. For whatever reason, you might want to do a thermonet to not have these placed on the outskirts of the houses. And you do that simply by having a shared energy source, connect the houses with a thermonet, and then you get a heat pump on the inside of the building. So nothing is visible on the outside because the pipes are in the ground, and you will have the heat pump inside the house. The Thermoroad is a little bit different here because we have a very big manhole for a lot of monitoring instruments. So there is something visible on the Thermoroad. It looks more like a bunker in these times than a technical installation. But I can assure you, you can avoid that in future projects because you don't need all the measuring that we're doing here. So when you have the heat pump inside the house, normally in Denmark, when you do newly built, you would install underfloor heating, and that's what the heat pump will usually supply. And that means it can go with a very, very low supply temperature, probably down to, if you want a low room temperature, you could go to 25 degrees for your underfloor heating, or else it might be around 30 or 35. And that's, of course, a very, very low supply temperature that makes sure that the heat pump can run very efficiently when it's upgrading the temperature from ground to room temperature. And it's not shown on this schematic, but of course it produces hot water at around 50 degrees, whatever you need to have a warm bath. So in each of these houses on the Thermoroad, you could have a normal geothermal heat pump. For this specific project, they have used a newly developed heat pump that's quite innovative for exactly this purposes. Metrotherm, who has supplied the heat pump, has actually developed it specifically for systems like this in mind. It's a propane heat pump, so it's already running on a refrigerant, which is which has a very low global warming potential. So that alone is a very nice thing for a heat pump to consider. It has a 4 kilowatt effect, so it's not suitable for bigger houses at this configuration, but it's very ideal for small and newly built. It has, as shown in the picture, a separate buffer tank because it's an on-off heat pump, so it needs to prolong the lifespan of the heat pump. It needs a buffer tank, so it's not going on and off all the time, supplying heat for the buildings. And it has a hot water tank, as nearly every heat pump needs. But one of the very interesting things about Metro Delta is that it has a temperature range down to -15 and up to +50. So you can put temperatures from PVT panels directly into the heat pump, and it will also prioritize if you can utilize the heat directly without the compressor, or if it has to do a lift on the temperature. Having a heat pump that can go all the way up to +50 is fairly unique in the heat pump market right now, but I have been told it's a feature of running with propane, so it should be possible a lot more in the future. And that's, of course, very nice if you want to utilize waste heat, which is a feature of the Thermonet, that you can say it's not utilized to its full extent in the Thermoroad project, but it's demonstrated, and it's something that can be tested in the future by connecting some type of heat production unit to the manhole. And as I mentioned, it works with PVT panels for a combination in an energy community, for example, and it has internet connectivity, which is also, as we see it, a mandated feature for anything running on a Thermonet. If you want to have swarm control, you need to be able to contact the heat pumps. And its most striking feature, at least on my perspective, is that it has extremely competitive prices. I have a couple of times experienced installers investigating what the price is of this heat pumps, and they're quite surprised at how low a purchase price you can get this heat pump for. But I know Flemming will show the economics later, and it looks quite nice. Now it also has, and I didn't really mention that when I walked through the list, but it has inbuilt passive cooling. Often that's a module you would have to purchase separately or buy a specific brand of heat pump to get passive cooling inbuilt in the system. But it's integrated in the Metrotherm Delta, and what this means is that it has a control function that can communicate with your underfloor heating system and tell it that it will be providing, instead of a hot source, a cold source. And the underfloor heating system can then take advantage of this colder temperature and use it to cool down the house in the summer. We haven't had too long a period, I think one single summer in 1 or 2 houses. I know Christopher will probably show some data from that, but my personal experience having a system like this for 10 years is that it's a very nice add-on to your house, so it doesn't overheat in the summer. It's something that I think we will have to talk a lot more about in Denmark in the future. And that's probably one of the reasons why you would want to make a Thermonet, is because it has good economics. And I've been working a bit with Flemming on getting the economics in place for the Thermoroad. So looking forward to see him present these data. Yeah, I think that was my presentation. I'm open for questions if there are any.
Anyone?
It's awfully silent.
Can you maybe just sort of summarize briefly the experience with Thermonets in Denmark?
Yeah, I can, because I think in Denmark, the first pioneering projects we had in Denmark was built around 2006. It was 6 houses in the northern part of Denmark, and it wasn't really talked about that much. Then in 2017, I was working in 2 projects that we thought we were demonstrating this for the first time, but we weren't. We weren't just aware of it at that time. We did a project with 15 houses in Silkeborg, and we did a project with 3 houses near Billund. So it was 3 houses, a retrofit system, and it was 15 houses in a newly built environment. So these demonstration projects was where talk about Thermonet in Denmark really picked up. And in 2020, we formed this non-profit association, and we have tracked down other Thermonets that were already there, and we've also encouraged people to build more Thermonets. And I don't have the exact count today, but I think we are around 20 systems in Denmark now. Sometimes small systems and also even big systems pop up that we don't know anything about. And at least to me, it seems like more Thermonets are coming, especially as we are seeing now, we have the legislation sorted out in Denmark. We are seeing external companies want to do energy as a service, where they provide these Thermonets. At least it seems there are 3 companies coming. And we also follow this on the international scene. I could have brought some slides showing that this is fairly well mapped out in Germany. I think there are at least 50 systems in Germany, and I'm guessing there are much, much, much more that we don't know about. I've recently talked to a small consulting firm in Germany that had already done 3 or 4 systems, but they are mainly for newly built. Retrofit is still difficult, but it appears that this is like a no-brainer for newly built. It's the obvious choice if you know the technology. So that's the main work we have done in Denmark, and we're now doing in the EU, is to raise awareness about these systems, because it is really the obvious choice that you get both heating and cooling. Yeah. So I managed to say something that raises questions.
So, and it would be fair also to mention Kensa.
Yeah, exactly. In the UK, Kensa has done a lot of work. Kensa is a heat pump manufacturer that has turned into a utility company, and they're doing a lot of work to spread this. And as far as I've seen, they have also tried to do it for retrofit, and they have primarily ended up supplying it for newly built for now, as they are sorting out the regulatory issues in the UK. Yeah.
Tools?
Yes, thank you very much for this presentation, Søren. Could you maybe tell us a little bit more about what needs to be done in order to make retrofits work better, or to take off better? Because I think I'm very I very much agree with you that the new build is very easy and it's very obvious very often, but where I think the main issue here is to make it work excellently for retrofit as well. Yeah,
and of course this is where I would take in the energy communities. It's an EU, it's a kind of actor that we know very well in Denmark, from the water supply, the heating supply, and the electricity sector. We have all these cooperatives running the Danish energy system. And basically, it seems like the EU is putting forward an actor that should work in basically the same way. So it's a group of citizens that can work together to buy electricity production equipment like windmills, solar panels, but it's technology neutral. So whatever they could agree on buying, they can put it up, and they can take up the energy at cost price. And naturally, that also works for heating and cooling. So in Denmark, we have, as you know, specialized legislation for district heating. But because the Thermonet is outside of this specialized legislation, it would be quite obvious to include it in energy communities. And in Denmark, at least, we lack a proper legal framework for energy communities. We have not implemented the EU directive in a proper manner yet. We are obliged to do so, and I'm hoping that we will stop playing games with the energy communities and actually rediscover the way we built the whole energy sector in Denmark by, for example, providing some kind of loan guarantees for these systems. Right now in rural areas in Denmark, people are a part of the municipal loan guarantee for collective heating systems in the cities. But when we are in rural areas, there are no loan guarantees available for collective systems. I think that's a major issue. So that would make, I think that's and Bjørn can probably add something because he is a social activist. So he knows how to rally people towards a common goal. And at least as far as I see it, these energy communities are right now a little bit stuck on financing. And of course, maturity of the value chain. There are a couple, there is at least one first of a kind project in Denmark that's like used as an example of what it costs to build these systems. But we can't base our calculation on first of a kind systems. We need a mature value chain, both on installers and of course the more, I don't know, the digging companies. That's basically the primary hole we have in the value chain right now, is the people digging down the Thermonet itself. Yeah, there's a long answer.
Ellie?
Hi, yeah, I'm an engineer in the UK, and we come across Kenza a lot, especially in Plymouth, where we've been planning a 5G network for some time, and we've just got some government funding. I was wondering around, what do you most frequently see as the heat source in live projects in Denmark?
Yeah, so what we see as the most common heat source is the shallow geothermal boreholes. And for some reason, that was because it was easier to do this on newly built projects due to space constraints. What I see the biggest potential of is, or let me phrase it in another way, for retrofit in rural villages, we have quite a lot of space, and it's significantly cheaper to do horizontal pipes than vertical pipes. So in rural villages where the cooling need is not that great, I would say horizontal is what we see more of in the planning stage. The big picture in all of this is waste heat collection. So the primary energy source for Thermonets should be in the future waste heat from industrial processes, from remediation wells, from wherever we are pumping water and discharging it without extracting the energy first. But this is a major task, and it probably takes some political initiative to make sure that this happens. But this is definitely the most energy efficient way. And it also invokes the storage capacity of geothermal in a way where it's not probably utilized right now. Yeah.
Thank you.
And final question, Bjørn, or comment or whatever.
Yeah, it was a comment in addition to you, Troels, to what Søren said. It's important to realize I'm building apart from other things I do, I'm trying to establish a local energy community. But the thing is, with Thermonets, you have a total cost of ownership that will be lower than any other solution. The problem is that that has to do with the lifespan of the Thermonet, which is documented 100 plus years. So that means that you need to have financing in place. You also have to make sure that you really want to build it where you build it. So there are some planning issues in that. And then the other thing is that the total energy efficiency will always be better for heating and cooling than any other solution you can come up with. I haven't seen anything better. And the main part is that if you need the passive cooling, it's a factor 10 to 20 more energy efficient. Experts can say more about this than I can. But those are the two economic and planning issues that needs to be taken into account, and it very much has to do with financing and interest rates.
Troels, just a quick reply.
Yes, I would just reply to that because I very much agree with you. What I think is the most interesting thing about the Thermonet is maybe not so much the efficiency, but the ability maybe to address the financing issue here, because as Søren mentioned, in many rural areas, the financing of heat pumps is the real deal breaker here. And if you put this into a Thermonet or into a energy community system for in some kind, I think we will be able to address this problem. So this is more a thing of organizing, a thing around the Thermonet that as it is, and not so much the Thermonet itself. I think is extremely interesting.
Yeah, and if I can just add a brief comment, I think you're right on the target there, Troels. That this is like the major issue for rolling out heat pumps. It's a financing issue. And this is why district heating has been so easy to roll out in Denmark, is because they solved the financing issue. So with energy communities having the financing, suddenly it becomes a lot more accessible to people to get heat pumps. Of course, with what the Thermonet makes possible is also everyone can get the geothermal solution, regardless of space constraints. Yeah, you need to take care of the time, Søren. So
I know. Okay, very briefly, Bjørn, then we close it.
Yeah, energy efficiency is very nice to have, but the real thing is that it's the key to make collective systems in areas where district heating should not go, because they will be energy inefficient. That's it.
Thanks. Okay, so we proceed. And now it's time for myself to present. Okay, so now we've seen the two technologies that are combined in Thermoroad, which makes it a bit easier to understand what it is that we're actually trying to achieve with this Thermoroad. So yesterday, the national TV, one of the national TV channels, did an interview with us, and I was sort of thinking on what is sort of the main idea in this? Is this just some crazy project that we've came up with, or is there some sense in it? And previously I used to work a lot with energy piles, which are foundation piles with embedded heat exchangers. And the basic idea in energy piles is that you use existing infrastructure, not just for one purpose, the thing it was sort of meant to. In case of energy piles, it's structural integrity of the building. But then you can start to add features to it, or new kinds of uses, in this case, utility. So when you do energy piles, you get, for relatively low cost, you get a heating and cooling system for your building. This is the same line of thinking, I would say, with the Thermoroad. That is to use this gravel structure that we're going to put in the ground anyway. We're going to use it for more than just structural integrity of the road. We're going to use it as a key component in a multi-utility system for the buildings around it. So that's the basic idea. So we have used this illustration extensively to explain what it is. And if we start from below ground, we can see we have the roadbed structure, this gravel structure that Michael introduced us to, this gravel that is compacted and engineered in such a way that you can put water into it and it retains its structural integrity. So in this roadbed, we have embedded geothermal heat exchangers. And these geothermal heat exchangers, as Søren showed, can be one of many energy sources for an ambient temperature shallow geothermal district heating and cooling system. So there's a dual use of the roadbed. One is as a retardation basin for water, because the gravel is porous. And the way to do that is to impose hydraulic control by lining the construction pit or the roadbed pit where you embed the roadbed structure with bentonite, a bentonite membrane that keeps groundwater out. It doesn't need to be perfectly sealed. You just need to be able to drain the water inside the roadbed quickly enough for it to stay dry, or so you don't have uncontrolled seepage into the roadbed. So the blue and red lines are the Thermonet, are the Thermonet pipes. We have a central manifold, which I'll show in a couple of slides. It's really big, where we connect everything and put in all the instrumentation that we also use in this project. So as Søren mentioned, this is only for demonstration purposes. This kind of manhole can be put below ground so you don't see it. We have 3 ball heat exchangers. It's sort of an oversized system, so we have a multitude of thermal energy sources, and these ball heat exchangers are mainly for backup and also to make sure we can do passive cooling, as much passive cooling as possible. And then a final perk is we also put a heat exchanger along the central wastewater pipe, very low-tech solution. We place a single U pipe that you use for the boreholes. We simply just place it along the wastewater pipe. So it's not a fancy pipe with an embedded heat exchanger or anything. This is something that is very practical and easy to do in practice. So the retardation capacity comes from the fact that at the end of the road, we have a water break. That water break can regulate the flow of water into the sewer. So that means that if we have an extreme precipitation event, water will flow into the roadbed. We don't use the permeable asphalt out here because the project was complex enough as it is. And the EUDP funds energy-related projects, so the focus is slightly more on energy here, but we don't forget the sector integration. So we use a traditional asphalt and simply drain the water into the roadbed by these drain grates on the sides. So there are drainage pipes inside the roadbed that are connected to the sewer via this water break. But the water break is restricted to just a bit less than 1 liter per second. So that means during extreme precipitation, the water level will simply build up inside the roadbed and then decay afterwards, so that we don't overload the sewer. So this is for planning purposes for the wastewater company that maintains and operates the sewer. This is something they can use when they are planning their systems. So it has some real value for them in terms of retention capacity. Okay, so on the surface we have the buildings, new builds. As Søren mentioned, these small heat pumps in each of the buildings, fully distributed heat pumps that provides room heating, domestic hot water, and passive cooling. And you simply have service pipes going from the main lines, as shown here, and you just plug your heat pump into it. And every building discharges their rainwater from the roof and so on directly into the roadbed. So we built this in full scale. And to do that, we applied for this project at the EUDP. We have these 6 work packages. Always you have project management dissemination. But the first one of the technical work packages, work package 2, thermal and hydraulic characterization of Vestergaardsmarken, dimensioning, instrumentation, and construction of the Thermoroad, and then data collection and analysis. So I'm going to focus on these 3 work pages. I'm not going to talk about the best practice because it's very specific to Denmark, but you can find it in the final report. There's a link to the reports in these slides, which will be shared with those attending the seminar today. Budget 7.3 million. It's not a huge project, and the project was initially scheduled, I think it was 4 years, but we had to get it extended for 1 year because we struggled selling the parcels, but we found a solution to that, which I'll get to later in the slides. So the project took 5 years, but please don't take this as it took 5 years to build this road. It wasn't that complex. It was actually much easier than we thought. So the site is located in Jutland, and from those outside Denmark, Jutland is the extension of the peninsula on top of Germany, and Copenhagen is to the east on the island of Zealand. We have Sweden to the east and Norway to the north, and Germany to the south of us. And the project areas is in the central part of Jutland. Just takes me around 20 minutes from Via and Horsens to drive to the site. So it's quite accessible for us. So when we develop these are municipal parcels. They were sold by the municipality at this time. That was sort of the original plan. We had to deviate from this. I'll get back to this at some point. But 6 municipal parcels, around 870 square meters each. And so for the first part of the site investigations, this is sort of standard practice. These shallow geotechnical drillings are carried out. And we took our hand drill to the site and took these hand drilled samples back to the lab so we could do soil sampling and measure different properties, thermal properties on these soil samples. This is important because remember this thermonet is placed in the shallow subsurface around 1 meter's depth. So to understand how the system behaves, we need soil samples from this depth, and we need to understand the thermal properties of the soil at this depth. So the company Land and Plan did the development of the site, the sort of the utility development that is required to plug in the houses. You need fiber net, you need electricity, you need wastewater, you need all this stuff, and Land and Plan was in charge of this. And this is the drawing they made of the Thermoroad system. So it's basically, if you're viewing the illustration I showed previously from the top, then to the left you have the 3 borehole heat exchangers that are placed in a field just to the west of the road. Then you have the manifold, the manhole with the manifolds with the red dot, sort of the large red circle. And then you have all these pipes that are embedded into the roadbed. These are single-use pipes that were simply it's the 1U pipes you've used for borehole heat exchangers, but here you can use them as horizontal heat exchangers by simply pulling them apart a little bit and creating some distance between the 2 legs of the pipe. Then you have the service pipes for the consumers. We have the main lines running in the northern part, edge of the road. And then you have the service pipes going into the different parcels. Under the road for those to the south, the parcels to the south, and directly into the parcels to the north. So one question I always get about embedding geothermal pipes into a road structure is, aren't those pipes going to crack? And that might be the case if you use the wrong pipes. We went with pipes that are resistant to cracks, PE, RC pipes. So PE is just a PE pipe. The RC means resistant to cracks. So they have a much higher pressure class, and they are more resistant to cracking. So I did a small analysis of the structural integrity of these pipes. I'm a geologist. I'm not a geotechnical engineer, but I'm able to find the equations and sort of do some investigations of like a worst case scenario. And the worst possible scenario I could think of is if we take a truck that weighs 40 to 50 ton and we simply park it on the road and just leave it there and then see what's going to happen with the pipes. The first thing I did was let's try and keep the pipes empty, no fluid, no pressure, no internal pressure in the pipes, and see how that works out. So I used the Boussinesq equation for a uniform circular load to compute the strains in the pipe at this burial depth of 1.3 meters, which is the case of the Thermoroad. And then you need the pipe characteristics, the overburden from the soil, tire pressure, and different other parameters. The Poisson ratio and modulus, what's it called, Young's modulus, to make this computation. So for a pipe embedded in the roadbed, you have the overburden of the road structure itself, and then you have the truck directly above it. And so we can compute the stresses at depth, the stress incurred by the truck and from the overburden of the material lying on top of the pipe. So you get the total stress of the pipe is around 61 kilopascals in this extreme scenario. So if we look at the buckling, when will this pipe start to buckle? We can use the equations by Timoshenko and Gehr from 1961. And the buckling, the pipe will give in on the short term if we apply just a bit less than 1 megapascals to the pipe in stress. And for long-term stress, this is lower because of creep effects. We're around 200 kilopascals. So we have a lot of overhead compared to the stress incurred on the pipe. For the short term, so if the truck is parked there for a few hours, the safety factor is around 16. For the long term, it's around 3. So we could actually apply 3 times as much stress to the pipe, even when it's empty, before it will start to buckle. But these pipes are pressurized, and so even if we park a truck on the road, if we pressurize at 2 bars, it's still dominated by an internal pressure. So you actually have to investigate what kind of pressure can your pipe withstand, the internal pressure of the fluid. And if we look at the pressure inside the pipe in this particular scenario, it's about an order of magnitude smaller than the maximum stress that we can have in these types of pipes. So just to summarize, we can safely place a truck on top on these pipes because internal pressure dominates if we pressurize at 2 bar. This is sort of what we normally pressurize this fluid at for these systems. And the pipe is still in tension. It's not being compressed because of the fluid pressure, and the tensile hoop stress is deep within safety limits. It's like an order of magnitude from cracking. So when we use these well-known methods, I would say it's safe for burial. These PE RC pipes are safe for burial in a roadbed, even if we have very, very heavy traffic on top. So that's just to sort that question out before it's asked by the audience. Okay, so just a few pictures from the construction. This is in the early phases. It took 12 weeks to construct the road in total. And so here we have the excavation pit. We can see the main lines for the Thermonet in the left side. different manholes that are necessary for different utilities are shown. And in the very back, you can see the concrete manhole for the water break. One of the things here was that we needed to keep the pit clear of groundwater. So that's the small pipes you can see to the left. Those are drainage pipes to keep the excavation pit from free of groundwater. So here you see the main lines again, but now from a different angle. Here you can see the service pipes. Service pipes go below the roadbed. They are not embedded inside the roadbed. You have the service pipes for the northern parcels where you can connect them directly, and then those that go below the roadbed and to the opposite parcels on the other side of the road. Here you see the gray bentonite mats that are used to seal the roadbed to keep this groundwater out once constructed. You can see the horizontal heat exchangers placed. You can actually you can tell it's these 1U pipes because you have a 180-degree bend, and then the two legs of the U pipes are pulled apart and held in place by these sandbags, as you can see here. And gravel has been added at some parts of these pipes here. So to the left, you can see the drainage pipes that where water is drained to the water break. You can see the concrete manhole in the top of the picture. So the drainage pipes eventually will go into the water break inside it. So at the other end of the road, there's a place to turn your car here if you have to go around. So the horizontal heat exchangers come here from the road and up to the manifolds in the top of the corner where you see all the pipes, all the loops of pipes that are lying around. And the road starts here in the bottom part of the picture. And two types of gravel has been added. I'll get back to that later, why we use two types of gravel. You can sort of tell there's something that's quite gray, something that's sort of more sand-colored, more brownish at the bottom. So here you can see a very clear view, sort of a transect of what the roadbed actually looks like. So you have the bentonite membrane in the bottom. That's easy to distinguish. It's quite clear to see this isn't sand or anything. Then you have the pipes directly on the bentonite membrane. Then you have a certain type of gravel that these pipes are embedded into, which is extremely rounded. And this is to prevent cracking. If you take the upper gravel, this is not rounded and more sharp. We have these sharp edges. So it's simply to protect the pipes that we add this very soft gravel in the bottom. But it has the same properties as Mikael mentioned. It has structural integrity even when being saturated with water. So the roadbed can retain two consecutive 100-year precipitation events. So this material, as Michael said, it has 30% porosity. So in total, we can retain, if the road is empty, we can retain 200-year precipitation events. So that's a lot of water, And obviously there's some synergy with the heating and cooling system here because all this water, it adds energy, but it also ensures that the thermal conductivity is high between the ground and the pipes because water saturation improves thermal conduction in soil. So this is when we were drilling the borehole heat exchangers. This is the drilling rig. This was Søren who was responsible for this. And here just some final pictures. Up in the left corner, you see the 1U pipe that is buried along with the central wastewater pipe. Very, very simple, pragmatic solution. Did not take a lot of man hours to do that. Again, a clear picture of the roadbed excavation pit with the pipes and the gravel. And down in the left corner, we have Hans-Erik, my colleague, and the thermal response test that we did of the Borehole heat exchangers. So this is a way to infer thermal conductivity of the soil along the borehole heat exchangers, and also the thermal resistance of the borehole itself. And finally, this 2.5 meter manhole with energy meters and a central circulation pump for that we determined we needed just for backup if we couldn't create enough circulation with the heat pumps, but also to bypass so that we can charge the borehole heat exchangers during summer because the roadbed gets quite hot, so we can circulate water from the heat exchangers in the roadbed to the borehole heat exchangers. So just to summarize the instrumentation that we did, we have energy meters, Kamstrup energy meters, these high quality energy meters on the brine side of the 12 heat pumps. Each of the 4 heat exchanger groups, so we sort of divided the heat exchangers into 4 groups. We have 2 groups of pipes in the roadbed, then we have the borehole heat exchangers, and then we have the heat exchanger along the central wastewater pipe. We have dynamic valves on the 4 heat exchanger groups, so we can open and close them. A central pump, as mentioned, to bypass and charge BHEs with the hot roadbed in summer, as mentioned. We have a flagpole antenna that collects and distributes data for easy access. And then we have a professional weather station that's located 880 meters from the Thermoroad site. This is quite nice because this allows us to get a very good understanding of why the buildings, these particular buildings, consume the heat they do. Because it's when you have to do that detailed analysis, you need very local climate data. And it's possible for us to get that data from the sites. So Energy Machines, who were partners in the project, I listed partners, I forgot to mention them, but they are in the slide that I started out with. The partner Energy Machines, which is a heat pump supplier and installer in Denmark, were supposed to provide online data platform and controls. But because of this type of project, which is a full-scale project, we had some technical issues with the manifolds that you can see in the top picture. They were made in metal and the rest is made in PE. And those two things just didn't work together. It just kept leaking. And so they had to use some of their budget on fixing this because they had the expertise to do it. So it's better to have a working system rather than having a system that doesn't work, but where you have a fancy online platform. So it was simply a way to prioritize the budget in the project. The system was commissioned in August 2024. And it took a long time to commission the project, but that was mainly due to the lack of sales of the parcels, not from sort of technical, practical issues. I'll get back to this. So we did further investigations to sort of cover the research parts in the project. Already mentioned this thermal response test and thermal needle probe. That is basically the 2 methods you use to quantify the thermal properties of the soil that ultimately determine how your district heating and cooling system is going to perform. So the principles of these 2 methods are identical. So for the thermal response test, we simply connect this instrument that you see on this picture to the borehole heat exchanger, and then we create a closed fluid circuit that goes into the instrument and into the borehole heat exchanger. There's a water heater that we can turn on, and then we have a Kamstrup energy meter. So basically the test is to circulate water that is continuously being warmed, and then we measure the temperature response of the borehole heat exchanger. We aim to dissipate roughly 40 to 50 watts per meter. So we measure undisturbed temperature profiles in the borehole heat exchangers. They look like what you see on the left. So in Denmark, we're around 9-10 degrees in the subsurface, close to the surface. Once you get down to a certain depth, you can sort of start to see the geothermal gradient temperature increase with depth. Then we measure temperature profiles after the test, mainly to see if there are groundwater flow effects on the borehole heat exchangers, where you can often see this as a sort of increased cooling of the borehole heat exchanger following the test. So to the right, you see the temperature increase in the borehole heat exchanger during the test, and you see the thermal effects. That's the green curve on the borehole itself. So we can use that to infer the thermal properties of the soil along the borehole heat exchanger, again, which is important for the performance of the borehole over decades of supplying heating and cooling to the buildings, and also the thermal resistance of the borehole heat exchanger. So we use software developed at VIA to interpret these testing data and do this sequential interpretation where we estimate parameters using more and more data from the test. Hopefully, we see sort of a convergence of the estimates of soil thermal conductivity. So for these boreholes, we have clay sediment, so we expect a sort of a low thermal conductivity. We're around 1.6 watts per meter Kelvin. That's quite low, especially if you come from outside Denmark and you're used to hard rock, granite, and so on, where it can easily be twice as high. Borehole resistance is roughly what we expect, around 0.15 for these type of borehole heat exchangers. So to sum up the site characterization, first of all, if you look at the borehole heat exchangers, we get these around 1.6. If we look at the wastewater heat exchanger, it's buried in wet sand, so it's quite a bit higher, around 2.2 watts per meter Kelvin. For the roadbed heat exchangers, around 1.5, a little bit lower than the borehole heat exchangers. The heat exchanger thermal resistance is as expected for borehole heat exchangers. It's typically around 0.1 to 0.15. It's lower for the pipes that are embedded directly into the ground, so to speak, in the roadbed and the wastewater. They're about 0.06, 0.07. So there's a better thermal contact if you bury the pipes directly into the ground. You don't have a borehole with a grout inside it between the fluid and the ground. We measure thermal conductivity around the depth of burial. We can see water content increase, and with water content, the thermal conductivity also increases. So this allows us to characterize all the thermal properties that we need for the grid, and for the heat exchangers that are connected to the thermal net. So these, as I mentioned, just to go back to some of the issues we struggled with through the project, which was basically selling these parcels one by one. At some point during the project, we realized we had to take a different path and get around this problem of selling these 6 parcels one by one. And we agreed to contact private developers in local housing developers to see if they would have some sort of interest in sort of taking over the project and build buildings on the parcels. So very quickly, and this was spearheaded by the municipality. Actually, they had good contacts with local developers, and very quickly we got, I think, 2 who were interested in the project, and the first one was GS Bolig. And they built 12 118 square meter single-family rental houses. So on each of these parcels, they built these sort of duplex buildings with 2 single-family houses on each. As Søren mentioned, each of the buildings have Metrotherm Delta ground source heat pumps, and we started commissioning the whole sort of system in August 2024. So Christian, who was not able to attend today, who's the CEO of GS Bolig, he says basically this is the value proposition for him. The possibility of cooling the homes is a big plus, and also the whole concept of a shared geothermal heating system, which at the same time contributes to solving the great challenge of the time with too much precipitation. That's interesting to him. So he thinks it's a unique system, and it's great if it can become sort of a financially viable solution for us to use elsewhere, as he says. And we'll shed some more light on this when Flemming is presenting later on. Søren has already mentioned the Delta heat pump, small heat pump, wall-mounted, same size as a wall-mounted gas boiler, and propane heat pump, high temperature range for operation, so it can supply both space heating and hot water, passive and active cooling, and PVT panels, but also Thermoroad. So it's sort of designed for those two purposes. So just to conclude, we've successfully, I would say, combined shallow geothermal district heating and cooling with a sustainable urban drainage system in full scale. The construction of the subsurface infrastructure and the road pavement, it took just 12 weeks. There weren't a lot of surprises in it. It was easier than I thought it would be. Embedding geothermal pipes in the roadbed may seem risky, but the analysis shows that we can safely do this. We are deep within safety margins for these types of pipes, the PE crack-resistant pipes that we use. The system now supplies 12 single-family houses, heating, cooling, and surface water management. And there has been no operational issues so far. GS Bolig is asking us to come up with an offer on a new system. They just recently made contact because they are quite happy with it. So I think that's very interesting. So future development should focus on thermal regeneration of the ground to minimize capex and subsurface infrastructure, optimal integration of cooling in buildings. I think that's been one of the biggest issues we had, is figuring out sort of how to get the heat pumps to work properly with the ground floor heating system to provide cooling also. Heat pump design and controls to minimize operational costs and integration with local electricity production. Cool PV or PVT and storage. It's going to be interesting when we can use our EVs to store electricity also and sort of integrate it into this context. Okay, that was it for my part. Any questions? Is everything clear how we did this and did it in practice? Okay, seems so.
Søren, I have a question.
Yeah.
What is the expected lifetime of these pipes that you have buried under the roads?
It's pretty similar to water supply pipes. It's the same type of pipes, and I think it's normal to say around 75 years. But I think there was a report, Søren, correct me if I'm wrong, but that was published a couple of years ago about new investigations of lifetime of PE pipes, which puts them at 100+ years. So you have a very long technical lifetime, but usually you can't depreciate it financially over such a long period. But there's certainly arguments for having a long depreciation period for the grid and the pipes.
Right, thank you.
Okay. Let's move on then, and it's me again. So now we move on to the Thermoroad tool, which is a design tool that we have developed in the project. I'm going to do the best I can to present this in the best way. A proper introduction to this would probably take a bit more time, but I've sort of tried to make it as understandable as possible for the general practitioner, and hopefully you can see why this can be important, especially in the early phases of the project. So okay, so PyThermonet is, as the name suggests, it's a Python library that will enable you as a practitioner to do a fast design / screening for new Thermonet projects or 5th generation district heating and cooling projects. That's sort of the aim for this tool. When a couple of years ago I was doing a summer school at Delft University, and I had to do a presentation on how to design these systems. And while I was doing that, I sort of realized you can either use rules of thumb, or you can use very complicated software like Modelica that allows you to do very, very detailed simulation of these systems, which is very nice. The problem is it takes a very long time to set up these models, and it's not convenient for a practitioner, and it's not very cost effective. You need some sort of middle ground where you can get some quick estimates that are better than what you can do with sort of rules of thumb. So PyThermonet is a way to sort of address this gap. And I'm going to present this now, how it works. So when we are in the early phases of a project and we need to figure out, is this going to work? Is it not going to work? Is this even feasible? And so on. There are some indicators that we need to establish to get an idea whether it's going to happen or it's not going to happen. We need some assessment of technical and economic feasibility, and we need a tool that will give us that with very little effort. So what does that imply? If we need some understanding of the economic structure of a project, we need the topology. We need to know how large is the grid, how many meters of piping do we need, and we need also to understand how big those pipes are, because bigger pipes are more costly in terms of trenching and also per meter of material. We need the length of the ground heat exchangers. So if you do boreholes, the only way to estimate cost of a borehole is to understand how deep should I drill. If you need to put horizontal pipes, as we have done in this project and other projects in Denmark, you need to understand how many meters of piping you need to put in the ground. So PyThermonet does not compute costs explicitly, but it facilitates the computation of different metrics that that are of interest in this case. It could be levelized cost of heating, levelized cost of cooling, capex, probably mostly capex. OPEX, we make some assumptions, but you can certainly get a pretty good estimate of capex. PyThermonet is, once you've set it up, it's very fast, so it's easy to do sensitivity analysis. That means if you look at your different parameters that determine your costs, you can do an analysis to show if I have some money to do some either field investigations or other types of investigations to narrow down my estimate, then PyThermonet can tell you which parameter you should focus on, whether it be the heating and cooling loads in the buildings, thermal conductivity of the soil, and so on. PyThermonet can be set up to provide you with that kind of information. So what kind of dimensioning parameter do we have for these systems? So it's a good way to think of a Thermonet as a ground source heat pump system, where you have ground heat exchangers that you need to size according to some criteria. You need to be able to supply what is needed in the building in terms of heating and cooling. The consequence is that temperatures, if you're in a heating dominated area like Denmark, is that brine temperatures are going to decline, ground temperatures are going to decline, and eventually your brine will become so cold that it can start to freeze the ground. This is what we're trying to avoid. So in the Danish ground source heat pump regulation, brine temperature is sort of the dimensioning parameter. So the average temperature of these systems cannot drop below 0. And that's sort of the average. Like if you take the average over many decades, it has to stay above 0, and that's because you need to avoid freezing the ground. The inlet temperature is allowed to go below 0, but not for a long time. It's not stipulated how long that is. The inlet temperature cannot drop below -4. So our PyThermonet tool must be able to come up with some estimate of the brine temperature and use it to sort of size our grid. So we need a brine temperature model for the Thermonet and the heat exchangers. So PyThermonet is based on physics. It's based on analytical solutions to the heat conduction equation in cylinder geometry. We model pressure loss in the pipes using the Darcy friction model, which is the standard approach in engineering companies to compute pressure losses in pipes. And we use the Nielensky correlation to do that. We model, PyThermonet models the thermal interaction between ground heat exchangers. So if you have boreholes, closely spaced boreholes, PyThermonet will take that into account and how they interact thermally with each other. It computes brine temperature responses from 3 heating cooling pulses, an annual response, that's sort of the average annual response over decades, seasonal response, winter or summer season for heating and cooling respectively, and for peak loads as well. And this is done by using superposition, which is also used for computing the thermal interaction between the ground heat exchangers. PyThermonet considers temporal diversity in peak demands. So if you have a number of buildings, they don't have peak loads at the same time. So this is also taken into account using well-established methods. And the ground heat exchanger length is computed directly using a very robust 2-step method, which I don't think I have to provide the details for. It seems to work quite nicely every time. So these are the types of equations that PyThermonet solves. And because all of it is analytical equations, it's possible for us to create a very fast tool. So it's this type of equation shown up here, partial differential equation. This comes naturally if you impose energy conservation in the ground. You can develop these differential equations, and we have well-known solutions to many of them, so those are implemented directly into PyThermonet. So cylinder geometry is everywhere in Thermonets, whether it's for buried pipes, those are circular, bowl heat exchangers are circular, horizontal heat exchangers are circular, and so on. A lot of mathematical work has been done on this in the 50s and 60s, and we can utilize that to make very fast designs with PyThermonet. So we published a paper on the method. If you want all the gritty details, you can find it in this paper here, an integrated design model for ambient temperature district heating and cooling networks, published in Science and Technology for the Built Environment this year. So in terms of installation, you have to use the link that is provided here for GitHub, where you can find PyThermonet. There's a a green button when you arrive at this page. If you click it, there's a download zip option that you can choose, and that's how you download the software. On the page, there's also an explanation of all the variables that we use in PyThermonet, what they are. So that means you can link the code directly to the different parameters in your simulation. So I've just shown here for the brine, RHO is density and C is specific heat, and so on and so on. So all the parameters that are used in the example scripts, you can find an explanation on GitHub. And there's also installation options. I'm not going to go into too much detail with this, but for your convenience, I've included a guide on how to install it. I use this with my students. It's a pretty robust way of installing PyThermonet. There are many different ways of doing it, but this one seems to work every time. So you get the slides after the webinar, and you can sort of follow this guide. If you have any questions or anything setting it up, I would be happy to help you, but try and work your way through this guide if you want to set it up. PyThermonet comes with several examples. So once you have it set up, you can run the examples and see the results, and you can start to get an idea of how you set up these simulations. PyThermonet has two sizing modes, and which one you use will depend on how you, if you're a practitioner, how you work with these things in your company, as is. There's a full dimensioning mode where you have to specify all the heat pumps that are connected and all associated upstream connections for every pipe segment in your grid. And that you need to specify this to compute flow in the grid and the ground heat exchangers. And we need to compute flow to be able to compute the thermal response of the entire system. So when you do that, it dimensions your pipes, but specifying heat pump connections to the pipe segments becomes quite complex for larger grids and thus prone to human error unless you use consistent method to do it. There's also an aggregated mode where peak flow and dimensions are specified for each pipe segment in heating and cooling mode. So I've seen companies who do the hydraulic dimensioning typically in some sort of Excel sheet. So for all the pipes, they get the sizes and they get the peak flows. So PyThermonet can take such input and just do the thermal computation for you. This is a quite easy way to use PyThermonet. And then you simply only have to specify the aggregated loads for your grid. That is the total heating loads, not for each heat pump. So that's 2 lines if you have heating and cooling, 1 line if you have just heating. But that requires that you set up the hydraulic computations and flow modeling in a separate software. But I know that many companies do this already. So I'm going to show you an example. This is a Thermonet in Silkeborg with 15 connected buildings. Søren have already mentioned this. The system in his presentation, just briefly. 40 new build, 1 existing house, 6 bowl heat exchangers shown with green dots, and a topology, as you can see here, with forward and return lines, and the service pipes for the consumers. So setting up this system in Python using PyThermonet is you need to provide 2 files, text files that I'll show in a minute. They contain information about the heat pumps, and that's in one file. The other file contains information about the grid, the topology of the grid. So in the PyThermonet file, you need to define the heat carrier. I've just taken a sample of code here just to show you what it looks like. So you define a brine object, and that brine has some properties. It has a density, it has a specific heat, viscosity, and a thermal conductivity. And this is the way you define different objects for a simulation. So you then have to define your distribution grid. You need to define your heat pumps. You can see this in the example files, how it's done. I would like to show you one of these files, but they are too long. So that wouldn't be very practical. Then you configure the ground heat exchangers, whether it's boreholes or horizontal heat exchangers. And then you can run this full or aggregated load sizing of ground heat exchangers. There's example files for both full and aggregated load sizing of ground heat exchangers in the examples library in Thermoroad. So for the full dimensioning in the Silkeborg case, we need to specify each of the pipe segments, the SDR of the pipe, that is the ratio between the wall thickness of the PE pipe and the diameter of the pipe, the outer diameter of the pipe, how many traces we have that has this type of pipe. So we can have identical, that's typically for the connection pipes, and then the maximum pressure loss that we permit in this pipe, and that's a round trip total pressure loss, so it's out and back again. And then the flow that from the heat pumps that are connected to that particular pipe, that means for the main line, the one that connects to the borehole heat exchangers, that has to carry the flow from all the heat pumps. And then for different parts of your system, different branches, different flows pass through that pipe related to heat pumps installed upstream. So that's what's specified over here. So pipes must inherit all heat pumps upstream and those that are connected directly to the pipe. So for the heat pump input file, you specify the annual heating. That's simply the heating demand divided by the number of seconds per year. And then the heating intensity during winter. This is watts, the average watts over the heating season that the heat pump operates at. The peak heating, which in these heat pumps are on-off heat pumps, so we know that the peak loads are going to be 6 kilowatt because it's 6 kilowatt heat pumps for the new build, 10 kilowatt for the existing building. Then we specify the expected SCOPs for the different conditions, the annual, the winter, the peak. And then we do the same thing for cooling. We also specify the delta T for the brine in heating and cooling modes. So this is also a way to control pressure loss. If you have excessive pressure loss, you can increase the delta T in your simulation. There are also examples of these files included in Thermoroad. So let's skip to the results. So if we look at Silkeborg, and we try to do the simulation for how it's built out there. It's only used for heating. There's no cooling, so it's a completely heating dominated system. It's built with 120 meter boreholes, which totals 720 borehole meters. We get some estimates of pipe dimensions, which corresponds fairly well to what is built out there. So it seems to be a system that is designed well, and we get the corresponding pressure losses as well. So that's the upper portion of the output is the dimensioning of the pipes for a system. The Thermoroad itself, the distribution grid, supplies 37% of the peak heating demand. That's quite a lot, something that needs to be taken into account, obviously, when we design these systems. Thermoroad estimates 119 meters. These were constructed with 120 meters. So it seems to be consistent with how the system was built. And it performs quite well in Silkeborg. Elapsed time, the model takes just 0.5 seconds to run, so it's quite fast. And just some considerations when we look at how the system was built compared to a scenario where we had to design individual ground source heat pumps for each of these buildings. So if we did that and we used a German standard for that, we would need 1,345 borehole meters. So this great reduction in borehole meters is due to peak demand diversity and also the contribution from the distribution grid itself. So that saves us a lot of infrastructure in the ground when we do thermonets in terms of borehole heat exchangers. If we fully balance the grid, we can save further borehole meters. That is, we regenerate the ground during summer. Oh, okay. Computation time versus input effort. So run times are short, but as you can see, it takes time to generate the input for the model. I had a couple of students who were designing a thermonet for 124 consumers, and they used 5-6 hours to set up and validate the topology input. Installation can sometimes be a little bit difficult, not with the guide I've provided you, but in other environments. You need some basic understanding of coding environments. But please do not despair. PyThermonet is extremely well suited for integration with GIS environments. So we can get GIS environments to supply the input for PyThermonet. So we are developing a plugin for QGIS and also a standalone web platform integrates for rapid generation of input for PyThermonet and also model execution. So just briefly on the QGIS plugin. So QGIS is free GIS software. And we're developing a module where you can execute PyThermonet simulations and generate the input much more easily without all these input files and coding and so on. So this is a screenshot from this plugin. So it's a visual way of designing the system. And you can use building information and road features to generate your topology, and everything is sort of automated in the background, and you just get the results that you need quickly. Yes. And finally, this standalone web platform that we're also developing, which is where you don't need a GIS environment. You can simply just take your browser, open it, log in with your user, and we haven't released this yet, but this is the intention. And you can, within, I would say, 20 minutes, you can generate topology and buildings and so on, and run your simulations and start to work on a first design with all this input and so on being generated automatically. So if any of you are interested in either of these tools, I would be happy to keep you updated on it and let you know when new things happen and access is provided and so on. So just to conclude, PyThermonet is really fast. Once you have it set up, it's very fast. It's based on physics. It's a screening design model for thermonets. It can rapidly generate first designs and cost estimates. It couples well with GIS. UIs are in development to support rapid model setup and execution. And ultimately, high fidelity models can be generated automatically from PyThermonet. We're also working on that in one of the projects. So that was an introduction to PyThermonet. Are there any questions? Yes, Ellie?
Yeah. How well developed is the QGIS plugin? Is it ready for use or?
Not quite. Right now, we're testing it for using Danish building data and road features. But so it's not. If you use it in the UK, it's going to be difficult. We probably need to use OpenStreetMap's features and so on to make it work properly. In your case,
slightly different coordinate systems. I'd be really interested in that. We work with a software called FME sometimes, which kind of does a bit of QGIS manipulation, and you can build Python scripts in. So yeah, just be interested in hearing about the development of that.
Yes, I would be happy to keep you updated. So QGIS has a Python API, and we use that to sort of link the things together. We're working on OpenStreetMap's implementation in the web platform, and that's certainly also an option for this QGIS plugin to make it more usable outside Denmark.
Okay, great. That sounds great. Thank you.
Okay. I suggest that if there are no other questions, we just have 5 minutes break because we're just falling a little bit behind schedule. And then we continue. So let's say 6 minutes past 11. Okay, everyone back? Okay, Christopher.
Yeah, and I'll just share my slides.
So now we're going to see some data from the first year of operation.
Yeah, you see the slides, right?
Yep.
Yeah, perfect. Yeah, so I'm gonna talk about the performance of the Thermoroad, and we have roughly a year worth of operation, data of operation. And for some reason it doesn't want to. There. Yeah, okay. So the data itself, it consists of data from two sources. So we have energy meters in all 12 houses, and these registers the total heat flowing into the house and out of the house, the temperatures, the flow rates, and also the electricity consumption. It's worth mentioning here that the electricity consumption is both the energy needed to power, well, the heat pump itself, but also the circulation pumps, the auxiliary heater, and the controls, everything that has to do with the heating equipment. So this was sampled at a 1-day interval for the majority of the time period. And then from the 3rd of July, this summer, we changed it to a 1-hour interval sampling. The second data source is actually the data from the heat pumps themselves. So we have these Metrotherm heat pumps, as has been mentioned, and we have for 6 out of the 12 houses, we have quite vast data about the heat pump state. So if it's producing domestic hot water or room heating or whatever it's doing, the valve states, so we know how the how the liquid flows around in the system. We get temperatures at various points in the installation and pump speeds and stuff like that. And this is sampled at roughly a 5-minute interval. So we have these two different data sets that we'll work on. So we need a definition first of the seasonal performance factor. So we're mainly interested in deriving like the performance indicator of the system when heat is delivered to the houses, because in Denmark the heating season is the biggest season. We don't have as much cooling need as heating needs. So we define the seasonal performance factor, and this 4 here indicates that it says down here. I don't know if you can see my cursor though. Oh, anyway, that the work done, the electrical work, includes, well, the compressor, circulation pumps, control, auxiliary heaters, and so on. And then it's the amount of heating delivered or extracted from the thermonet plus the electrical work, which is converted into heat, divided by the total work done. This is slightly not true, because when we do passive cooling, we also use electricity, and we haven't factored that out in this W here in the work. So the SPF4 that we're gonna get is gonna be slightly lower than the actual value because of the electricity used when we do the passive cooling. So this is the data for, well, almost a year. And we see on the top panel here, we see how the temperature in the grid, it's these blue dots here, how it evolves with respect to time. I've taken the value after the heat pumps has been running, after a heat pump has been running for at least 5 minutes. Then I take the value that we measure coming from the grid. So it's not like as some of the brine standing in the house that has been heated by the house. We know that we have the flow in the system. And then we have the ambient temperature, so the outside temperature as well, and the precipitation. The lower panel is more interesting. It's the SPF 4, but for the individual houses. So I've indicated with these vertical dashed lines, I've indicated the primary heating season. Well, it should be from October, but we see here that some of the heat pumps, they don't perform that well at the beginning. Some of them were in just this auxiliary heating mode. So there are a few settings that had to be changed before we got into a stable heating supply. So I've calculated this seasonal performance factor between these two dashed lines, and we get a value of 3.47 from this period here. And it should be noted that we actually see a slight decrease in the seasonal performance factors, and this is expected because as the temperature in the grid decreases, well, the lift is going to be higher, and therefore the CUP or the seasonal performance factor is going to be worse. It's going to be lower because we need to lift the temperature from the brine to the house further. But then when the temperature reaches roughly this 10 degrees again at the other dashed line, what happens here, while the cups roughly stays low, is that, well, we don't need as much room heating anymore because this is the 1st of May. It's gonna be warm outside. But the domestic hot water production is gonna be more dominant in this last part of the year. And because the domestic hot water has a higher lift, then the seasonal performance factor during this period is going to be worse. And that's why we see this decline in the seasonal performance factors. And then at the end here, we start to go into the heating season again, but we have a high temperature higher than what we started with, and that's why the cups shoot up, but we only heat in certain areas or certain portions of the time, and that's why it wiggles a lot. I also calculated the seasonal performance factor from the first dashed line until the end of the data set. And here, if we get almost the full year, we get a seasonal performance factor of 3.38. Yeah. I've compared these to the hourly or the instantaneous CUP values derived from the heat pumps. So the heat pumps, it had these 5-minute intervals, and I was able to compare these with the data from the energy meters and find like time periods of the energy meter. So this 1 hour time period where the heat pump had only been running in like a pure mode or only in a single mode. So only active room heating or only active domestic hot water production, or this active domestic hot water production and boost where the auxiliary heater is turned on. And when we do this, we get this distribution of CUP values. And these are more spread out due to transient effects. So because we are close, or we are at the sampling limit of our data set, then the heat pump can turn on like at the end of a period or being turned on at the full period. So we have like some spread in the values. But the important part to see here is that these SPF4 we had here at the previous slides, these are sort of the average value, or they're at least between the CUP value for the active room heating and the active domestic hot water production, as we would expect. So we would expect the active room heating to perform better than the domestic hot water production, and that's also what we see when we go down at the hourly level. Yeah. So now we move on and look at the cooling part, and I've defined this seasonal performance factor of the heating and the cooling as this expression here, where we basically just added the cooling, the total amount of cooling that we have done in the system. And the cooling is the heat rejected to the thermonet. So not the heat extracted from the house, but the heat ejected to the system, the thermonet. There's a slight difference here, which is the electricity needed to run the circulation pumps, because that will go from into the liquid when it's in the system and then out to the thermonode. So the heat rejected to the thermonet is slightly bigger than the heat extracted from the house. Anyway, here we see again the same plot as we saw before, but it's the seasonal performance factor of the heating and the cooling down here at the bottom panel. And now the two dashed lines indicate, the first dashed line, the leftmost, indicate where we turn on the heat cooling for two of the houses, and you immediately see that these lift off from the rest of the houses and go up to around, the highest is just above 9. Normally for this passive cooling, you would expect an EER, energy efficiency ratio, of maybe 20, something like that. But this has to do with, we don't see that here because we also have the domestic hot water production into this factor, the seasonal performance factor, so we don't get the 20. But we get like some sort of, not average, but a mix of these two. And we can't separate these with the energy meters that we have. The second dashed line, we turn on more of the cooling, or in more of the houses, we turn on the cooling. And here we see that, again, the seasonal performance factor shoots up for these houses. I've also looked at the total heat delivered to the net, to the thermonet, and this is then shown for the different houses here in the figure, where I've taken two different dates and divided the data into this, because some, not the majority, but some of the houses had their heat turned on at this August the 20th, so we could see the difference between those. So the total heat delivered to the net in this case was 2.7 roughly megawatt hours. But because it was these two, the two leftmost columns here indicate these two houses where we turned it on early in the season. So it was on June the 6th, which is roughly either 90 or 95% of the cooling season here in Denmark is from June the 6th and onwards. So these two, the two leftmost columns in the figure, cover the majority of the cooling season in Denmark. I've calculated the average of these two, which is this dashed dotted line that you see in the top third of the figure. And if we then say that this is the average value that we would expect from all the houses, then we can calculate the potential heat delivered to the net from all the buildings, and it comes out to this value of almost 7.8 megawatt hours. Yeah, there's a question, Søren?
Yeah, it's just the reason why those two curves are different, because we use cooling in both buildings, but there are different cooling settings. We're trying to figure out which one. I think one is low cooling mode and the other one is high cooling mode, and it's quite obvious here which one is which.
Yeah, exactly.
So probably the average should be more close to the larger bar.
You can definitely run the system, or it would be very likely that you could run all the systems close to the larger bars and not the smaller of the two bars, depending on the cooling setting you have in the house. Yeah, so as I said, the potential total heat extracted or delivered to the Thermonet would be this almost this 7.8 megawatt hours, which is roughly just lower than the annual heat drawn from the Thermonet of 2 houses. So I've calculated this, and this is up here, which is 4.7 megawatt hours roughly. That's how much heat each house on average draws from the Thermonet. So we can almost supply the heat of 2 houses from the cooling of all the houses. I've also looked at the efficiency. So this was where we compared again the energy meters and the heat pump, how they're running, and to indicate to find periods where we have different pump speeds in our cooling mode. So this is what the figure shows. It's the passive cooling effect, split into these 4 categories of how fast the house loop, so the circulation pump in the house, how fast it was running during that time period. And what I mean by dominant mode is that we had to have more time in a specific mode compared to all the others combined. So yeah, the undecided ones is where you could, for instance, have a third in 2 of them, and then slightly, and then a sixth in the 2 last ones, where you don't have a dominant mode. Anyway, what we see here is that our passive cooling effect is strongly coupled or related to the pump speed. So the higher the pump speed, the more cooling we have in our house, which we would expect because we get more flow in the floor heating or floor cooling in this case. It's also worth noticing that we have very few cases where we're above this 80% of the pump speed. And actually, we only saw 2 cases where we were above 95% of the pump speed, like that was the dominant mode. So this indicates that the system has more capacity for the majority of the case than is actually needed. So we can cool quite efficiently with this, or should be able to. Yeah. And that was actually what I had to present. So the summary is that this seasonal performance factor for the heating period, we got a value of 3.47. And if we took it for the extended season, which almost covered a year, we get 3.38. And we validated or compared these against the hourly CUP, which varies a bit more, but we saw that these values are between the CUP of our, active room heating and the domestic hot water production, as we would expect. And for the cooling, then during the summer of 2025, we saw that we delivered 2.6 megawatt hours of heat to the Thermonet, and could estimate that if we had the houses operate at the average of these 2 houses that had cooling turned on for most of the season, then we could reach 7.8 megawatt hours of heat delivered to the Thermonet, which roughly equals twice the annual heat drawn from the Thermonet of 1 house. So 2 houses could potentially be supplied by the cooling, the heat extracted during the cooling process. Yeah, that was what I had about the performance of the system. So if you have any questions, yeah.
Yeah, just a quick one, because I recall we had this meeting, and if I remember correctly, it was fairly late in this period we have measured, where we investigated that the spread of the COP values were quite large. So as if I recall correctly, this period, the SPFs are a bit lower than we would expect them to be for the next year, because we did some adjustments. It'll not raise it a lot, but it will be a little bit bigger than what's reported here. Am I correct in that?
Yeah, also, if we go back, you can see some of here. Yeah, this one. You see some of the heat pumps not performing as well, and we have a period here where a few of them drops close to 1, or one of them actually reaches 1. So you would expect that we could, well, optimize the controls of the heat pumps to avoid this.
Yeah, and I think we've done that at the after the winter period. So probably the winter period we're going into will have better values.
Yeah, that would be expected. Yeah, I think Henrik first. Henrik, do you have a question?
I think you're muted, Henrik.
Yeah.
Okay, maybe not.
Okay.
Otherwise, yeah. Illy, do you have a question?
Yeah. Have you been able to model or isolate the effects of precipitation?
No, not yet. I've only just shown in this graph to see if it had an impact on the temperature of the Thermoroad itself. But I haven't looked into how it's going to affect it. I haven't been able to model it yet.
Okay.
I can just comment on that. We actually built a prototype of the Thermoroad. We have 2 of these systems. And we did some modeling in that paper of the effects of, well, the sort of the recharge effects of having constant water supply. I can find that link for you.
That would be great. Yeah, thank you.
Okay, yes, I had another question also, or maybe not, just to clarify. So SPF 4 means, so you sort of classify different SPFs according to where you measure it, how much of the electricity consumption you measure.
Yeah.
This is basically sort of the worst one, because the electricity meter is sitting on the heat pump. Everything that goes on inside the heat pump that consumes electricity is included in these computations. So it's a very honest measurement, so to speak.
Exactly, and that's also why we see that it drops to 1 when the auxiliary heater is the dominant mode. So it drops to 1 here. So we also have the auxiliary heater in this SPF 4.
It's also interesting to see, if you go back to the slide with the, if you look at the new heating season we just entered into, there's only 1 heat pump that is operating now below 3. Whereas when we started, we had sort of like 2 ones that were sort of performing more or less worse and worse, and the rest of them are sort of high up.
Yeah, actually, at the start of this season, you have 4 that are really low, like at the previous season.
Yeah.
Yeah. And Henrik still has raised his hand.
Yeah.
Yeah.
I have 2 questions. The first one, to what extent can you store the heat from the summertime, from the passive cooling, and reuse it during the heating season?
So it depends slightly on which of the thermal sources that you use. But if you use the borehole sources and also in this case, it would be ideal to use the borehole sources, because there you don't have any flow of energy away from the system. So there you could store, I'm not sure quite how much, but like a big portion of it. Søren and I had a discussion where we talked about at least 80%, if not more, of the heat. But if you have it in the roadbed, then obviously if you're draining the water away, then you don't want to heat it up with this heat from the summer.
Yeah.
So there are some controls that needs to be in place to efficiently reuse the heat.
All right.
Yeah,
thank you.
just a quick comment on this. We actually modeled this effect also in the paper I just mentioned for the Thermoroad. And the impact of groundwater flow on storage at these temperatures is not so pronounced. So it does actually make a difference if you store some heat during summer. It's not it doesn't flow away with the groundwater.
All right. Thank you.
I will include a link to that paper.
Yeah.
Yeah.
My second question might be a bit out of the scope of this presentation, but I'm asking anyways. But have you also studied the user satisfaction from this passive cooling in the houses?
We haven't gotten to that yet. We put in some temperature sensors, but the problem is that when it's hot outside, people tend to open the windows, and so we don't have a fully sort of controlled environment. But TV2, the national television company who did the interview, said they couldn't get any of the people living in the buildings to participate in the interview because they didn't really care about it, and so that can be either good or bad. But I suspect if they had a lot of problems, then they would have been willing to sort of participate and say this is the worst system ever, and so on and so on. But no, we haven't done it yet because we have been struggling quite a bit getting this cooling and figuring out how to set it up, how to get the right settings, and so on. But for the next season, we're going to have it running in all the buildings. Right now, there's some valves that are not working correctly in the heat pumps. They all need to be replaced and so on. So we need a full setup with the full value proposition before we do the survey that I was talking about. So my plan is we need to get through the next cooling season, and then I will disseminate this questionnaire, and then we get some sort of realistic information about performance. Søren?
Yeah, a couple of things, and if I begin with the question you just reflected on, as mentioned, I've been running with this for 10 years now, and I've just passed a link into the chat. I'm a very happy end customer, and of course I'm also very, very much biased, but but it's definitely nice when you get it up running with the correct settings. There is a graph on the link that's objective data where the room temperature is measured in my house over a year, and it just stays almost completely flat during the summer. So I don't have these high peaks in temperature at my house, and I would expect it could be running similarly to what it does at my home in other houses. Then there was this question about storing energy, and there are, when you do energy storage on these systems, the main benefit, as far as I can see when I have calculated some of them, is that you can actually decrease the number of boreholes quite significantly if you can recharge them every year compared to if you keep extracting heat from them. So I did a bigger thermonet where I simulated different time periods, and you can almost halve the size of the bore field if you are able to supply the same amount of heat you extract every year. And that's quite a significant reduction in capex. So it's very significant that you can resupply the same amount of heat that you have extracted. And there are many ways of doing that when you are connected to a thermonet. And then just again a small thing about the SPF. So we have something that's not really there's something contributing to drawing the SPF down a little bit that doesn't have anything to do with the thermonet, and that's the size of the hot water tank in the houses at the Thermoroad. It's probably a little bit too small for some of the houses. It does it lives up to all the standards of how big your hot water tank needs to be. But some people just take longer bath than what's in the standards. And when you empty the hot water tank from a heat pump, it's difficult to fill it up. I think we say that when you turn on your shower, you will extract something according to 15 to 25 kilowatts of energy out of the shower head. And of course, if you have a 4 kilowatt heat pump with a hot water tank that's running down, you need to enable the boost function. And then you have the auxiliary heater stepping in and doing some helping. And we do see some of that in this system, that there's probably a little bit too much use of the auxiliary heater to help with the hot water supply. And that draws the efficiency down a little bit, where it shouldn't be necessary if you had a bigger tank. So it's just a small point of clarification.
Yeah, to add on this, for 2 of the 6 houses that we had heat pump data from, they were using the auxiliary heater for either a fourth or a third of the like total time that the system was on heating mode. That was also like that portion divided by the auxiliary heating time was like a third or fourth. So 2 of them, where the rest of the 4, it was like almost 0. So yeah, I guess that's it.
Yeah. Yeah, just a concluding comment. I think these SPFs are actually quite nice, and if we did the Carnot efficiencies, they wouldn't be bad at all. I think this is more or less what is to be expected of such a system. Maybe a little bit higher, and as Søren said, I think the next heating season will have slightly higher SPFs for the reasons mentioned here. Okay, so it's time to move on to Flemming to show the economics of the system.
Yes. Hello. Yeah, I will share my presentation about the economics of the systems. That was the wrong screen, sorry.
Wow.
Well, so, yeah. Do you see the presentation now?
No, we see something very crazy.
Yeah, it's like infinite mirroring or something.
Yeah.
Just maybe plug off screen 2 or something.
Yeah. What's this do?
Much better.
Now you see the presentation?
Yes.
Yeah. Yes, my name is Flemming, and I'm an assistant professor here at VIA University College, and I've been looking into the business case and the development towards commercial scaling. Yeah. So my agenda. I will just briefly describe the drainage system and the Thermoroad heating, so you have an understanding of how I divided the calculations. And then I will look into establishment cost of the Thermoroad itself with the drainage system and the Thermoroad, and compare that to the establishment of a traditional road. And then I will look into the investment and annual cost of the Thermoroad heating itself, like looking only at the heating part. And then in the end, I will look into some of the key takeaways I have from interviews with developers. Where I have some takeaways about what they think about Thermonet as a future heating solution. But just this is just a brief presentation. Yeah, I divided it into the heating cost of the heating system and cost of the drainage system. So first, I will take a look at what it costs to build this Thermoroad and only the additional cost of making this drainage capability that Søren and also Michael have already introduced that the road had. But just to get you some basic understanding of the settings I've been calculating on. So what you see here is the Thermoroad as is built with 12 residences. And what I compare it with is building a road, a traditional road that you can see is built over here with 8 residences. And the way I consider the calculation is that you start with a field, a bare field that there's no infrastructure on. So I take all the investment that you need to excavating work, preparation, drilling, to pave a road and establish such a road. I take all the cost associated with that and the heating system into account. So this is the expenses of constructing a road. What you see on the left here, 440,000 kroner is the price of establishing like a traditional road, where you just like excavate and you pave the road and you put down normal gravel. And what you see on the right is if you want to have this drainage system within the road, you see the price is almost or more than 1 million crowns higher. And that is for this specific project because there has been a lot of cost. There's been a lot of extra cost because it's first of a kind. And it's been noted that for example, the wastewater company have had extra meetings, more coordination that they would have normally when they're dimensioning a road. And they've also spent money on additional counseling consultants to establish this roads. So of course, when you do what the numbers show is that when you do a new kind of a road for the first time, there will be extra expenses. And as I've noted up here, you can see that 600,000 of the kronas have been categorized as unforeseen and or other expenses. So that's expenses that you don't see in when you build a traditional road that these types of companies have a lot of experience with. So here on the next slide, because what you also have to bear in mind is that the traditional road I'm comparing with had 8 residencies, but the Thermoroad has 12 residencies. So when you divide the total cost, you see that the cost will be just above twice the amount to build a Thermoroad compared to a traditional road. And then when we further remove these unforeseen and extra cost here on the right, you see that the cost equals more out building a traditional road compared to a Thermoroad. A Thermoroad would still be more expensive, but not as much. And still, we are only looking at the drainage system. And next up, I will show you calculations for the cost of the Thermonet, the heating system. So all these, the cost of the boreholes, the horizontal, the shallow heat exchangers, and the heat pumps delivering the heat to the system, and I'll be comparing it to a normal district heating system. Yes. Here you have the investment cost. So on the left, you can see that, and the investment cost is shown per residence. So on the left, this is the case from the project. You can see that it's per house you need to invest almost 95,000 Danish kroner to have a Thermonet, have a heating system for each house, each resident on the street. And you can see there are costs associated with equipment. Sorry, the first cost here is additional excavating work. So when you build a road, you will need to do some extra excavating work. You will need to dig half a meter further down and then install these pipes that Søren also introduced. And then you remove dirt, and then you have to replace that with this soft sand so you don't damage the pipe. So there's a extra cost associated with that. And then you also have a cost associated with all the drillings, all the equipments, the manifolds, the pipes itself, and so on. And then, of course, you also have the cost associated with the heat pumps, with the ground source heat pumps. Should we take questions in the end? I think, is that okay, Bjørn?
Just understanding, maybe you said it, but with this price, was that including the extra costs or excluding them, the unforeseen?
So this is only the cost of the Thermonet system. So as I said here, I divided it into, so the first thing with all the unforeseen cost, that was only about the drainage system. Okay. And now we're looking at cost associated with the Thermonet, the heating system, and here I have all costs included. Yes. And then we look at the cost of district heating. It adds up to 96,000 Danish kroner per resident, so almost the same. It's a bit less expensive in investment, but we're almost the same in these calculations. But if we look at a yearly cost, so the cost of the operational cost of running such a system per year, you can see a significant difference. The Thermonet, the user has to pay electricity for the heat pump to run to deliver heat, and what we've seen for deliver heat of 7.5 megawatt heat, the cost has been about 4,000 Danish kroner per user or per household for a year. Whereas if they would have chosen district heating, it would have been 11,500 Danish kroner. So that's quite a significant difference here. Sorry. And if we try to combine both the annual cost of the investment and the annual cost of running the system, so this is both CapEx and OpEx, we can see that there's also quite a difference. So both investing in the system and running the system will have an CapEx or will have an annual cost of 10,000 or almost 11,000 a year, assuming 6% interest rate and 30 years payback time. Whereas if you compare it with the district heating system, it would be almost 18,000 kroner. So that's quite a significant difference here. And that also is reflected in the payback time. So if we say, what is this additional investment that is in Thermonet compared to normal district heating, like how much time would that take to pay back if I had chosen the higher investment in the Thermonet system, the payback time it's 2.3 years. That was about the cost, and you will have time for questions. In the end of my presentation, I will just run through what some of the knowledge I got from the interviews from the developers I have been talking to. But also I need to mention that in these calculations, I have not calculated or included the value that this system also offer, like passive cooling, no outdoor visual heat pump, we have no noise, we have longer lifetime compared to air source heat pump, we have lower cost for service and maintenance compared to air source heat pumps. So these are also some of the value you get from the Thermonet as we see it. And that's also some of the key insights we got from the developers. I've been talking with 3 developers, including Christian Skifter from GS Bolig, and then Martin Novak from Tybo, quite a big developer also, and then a private building constructor consultant who builds his own houses, but also consults larger developers. And what they say is they dislike financial risk and uncertainty. They all said that they're all interested in the Thermonet. They thought it was really interesting and that it had something to offer, but they really don't like financial risk and uncertainty, and they want predictable monthly payments and prefer fixed costs. They want to know what to pay, what are the costs we have each month. And furthermore, they don't like too much upfront investment. That's unattractive when they have to develop. They already have to gather a lot of money for building the houses, so they don't want to have too much upfront money also investing in a heating system. And then cost is still the primary decision driver, but it's always in this relation to risk. So if something is too risky, it really has to be a good business case. And then unforeseen costs are of major concern, such as breakdowns in the systems. So they're also willing to pay more for a solution with known cost and little risk. E.g., for example, a solution with service contract. They sometimes tend to remove risk. If we look at technology preferences, then air source heat pumps are often chosen because today, when they have to develop, they often chose that because it's a technology they're very familiar with. They have it's plug and play solution for them. They know what they're getting, but they also see some disadvantages of it, as we already been talking about. That there is noise and there is the visual impact that is disliked, and there's high service and maintenance, which are seen as inconvenient and undesirable. Then LCA as a requirement is also something they highlighted. If they can get a heating solution with lower emissions during the life cycle time, then they can choose other materials or other places in their building and construction where they can emit more. So this is also something where they mentioned that air source heat pump and also Thermonet will have an advantage over district heating. Yeah, I think I'll just go to this slide. They like this energy as a service model, as they know from district heating, is very appealing to them, where they have that there's no high initial cost and they know exactly what they have to pay each month and there's little risk. They really like that, and they're looking for something similar to it. But I think when asked to the specific project, but they're also interested in knowing what is the actual cost, because I think when they see the TCO, the total cost of ownership, see these numbers, what they actually are, they might be interested in owning the solution themselves. And then 2 of the 3 developers I interviewed, they asked for a specific proposal on an upcoming project they had. So there's a really high interest in this solution. Yes. Conclusion. Thermoroad has a slightly higher initial investment than district heating. Annual operating costs for Thermoroad are significantly lower. The developers have a preference for a plug-and-play solution with low and known risk. So they are open to owning Thermoroad, but in favor of energy as a service model, meaning a small connection fee and that the user pay for consumption. And then Thermoroad draws attention and is seen as a promising solution, but the developers, they like to sit back and wait for broader adaptation, see someone else take the risk. They're really waiting for this technology to be as proven as the air source heat pump is what I conclude for the interviews I have had with them. Yeah, sorry, I didn't have so much time for my presentation, but I hope we have 3 minutes of questions. Yes.
Yeah, sorry for that, Flemming. We sort of took a little bit more time on the different presentations and so on. So, but I think you sort of showed everything that we need to know. Are there any questions or? Jan?
The price used for district heating, is that the local price? And if yes, what would it look like if we used a national average?
It's the local price from, it's called Hornslund Klimavarme. It's the local price, and I haven't compared with the national average. I think that's tricky to compare with, but I haven't done it.
It looks high compared to what I see elsewhere.
Okay, yeah. Søren, do you want to follow up to that?
Yeah, I just wanted to add that for lucky coincidence, we built this project in an area that was just developing district heating based on waste heat and a heat pump and some gas as a backup. So this is it's very hard to compare these systems with district heating, because often the district heating companies have been around for quite a while and have depreciated their assets, and due to legislation have much lower prices than their assets should justify. But for some reason we had this nice project where we were able to compare 2 greenfield solutions. And I think this makes the point that it would be much harder to compare to already established district heating, because what we also found when we were doing this, Flemming and I, is that a lot of the costs evade the calculations when you try to compare with the district heating. Often when the municipality makes a new set of plots, sometimes the pipes are already in the ground. So that cost is often evades the calculation, and it actually turned out to be quite a significant investment that developers often pay as a sort of contribution to making the plot ready, and it's put into the plot price. So I think that these numbers are actually the closest you are going to get to a fair comparison to district heating.
That will be important to communicate.
But if you have further questions, you're always free to contact me, and I'll be happy to share the calculations.
Okay, so we're 1 minute past the end of the meeting. So thank you all for attending. It was good to see sort of a full overview of all the stuff that has been done, and hopefully we'll see more of these systems in the future. Thanks all. Bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you.
Thanks.
I'll send the slides and all that stuff